Welcome back. Topic 3. Introduction to Turbulent Flow Convection. A. Define laminar and turbulent flow. First, this is a photo of laminar, photo of turbulent, sketch of laminar, sketch of turbulent flow. Laminar flow is defined as a highly ordered fluid motion. It indicates the fluid streamlines are parallel to each other. There's no mixing between them. Therefore, the transport of friction and heat between the fluid streamlines is carried by molecules. Turbulence, on the other hand, is defined as highly disordered fluid motion. It indicates turbulent fluid motion is full of mixing, swirling, tangling, and chaotic. Therefore, the transport of friction and heat within the fluid is carried by this large-scale vortex mixing. Second, we can use the Reynolds number to determine the flow pattern, whether it is laminar flow or turbulent flow. B. You may wonder, what causes a flow to become turbulent? The answer is, the first cause is the increased velocity and increased length. Based upon the definition of Reynolds number, if the characteristic length is increased, the laminar flow may develop into a turbulent flow, or the coming flow velocity is increased, the flow will become turbulent. The second cause is the small perturbations. It could be surface roughness or device vibration. For example, if flow passing over a rough surface, the surface roughness could trigger the laminar flow to become turbulent. The third cause is flow separation. Whether it is external flow or internal flow, flow separation creates a weak region. The flow in the weak region is turbulent flow. C. Then you wonder, why do we need or why do we care about turbulent flow? The answer is, the first reason we care about turbulent flow, we need to study turbulent flow, is that most flows encountered in the engineering applications and nature are turbulent. Whether it is galaxy, hurricane, or smokes in nature, or atmosphere behind wind turbines, weak region behind submarines, and combustion process within the gas turbine in engineering applications. All the flow patterns are turbulent flow. The second reason we're interested in studying turbulent flow is the turbulence is responsible for two unique motions. The first motion is intense mixing. The different color of balls represent different layer of fluids. Before turbulence, this is laminar flow. After turbulence, flow becomes turbulent, and the fluid particles you can see are well mixed. This indicates that the intense mixing will bring the fluid particle with different energy, heat, momentum into close contact. The second motion that turbulence is responsible for is a rapid fluctuation created by the swirling structure of different sizes, some big as airplane, some small as our size of hair. This swirling structures also called eddies. This rapid fluctuation will transport carry more energy and momentum to different regions of the flow. Therefore, due to these two motions, turbulent flow is associated with much higher heat transfer coefficient H value. And we want to know why. So that's the two main reasons we want to study turbulent flow. Then you raise the question, which is, what's the difference between turbulent flow and turbulence? The answer is they're the same, but they kind of emphasize a different aspect. To my understanding, turbulent flow emphasizes the difference from laminar flow, but turbulent flow emphasizes the difference from laminar flow, but turbulence specifically refer to the chaotic motion, the fluctuating, mixing, tangling, and the swirling. D. Then you wonder to yourself, obviously turbulent flow is different from laminar flow. Are we going to use different governing equations to describe turbulent flow? The answer is no. Turbulent flow will be described by the same governing equations as a laminar flow. The mass conservation, momentum conservation, and energy conservation. We have 5 equations, 5 unknowns. Therefore, the problem is closed, meaning we can get the unique solution with initial condition and boundary conditions. Then you keep asking, if we use the same governing equations to describe turbulent flow and a laminar flow, how do we describe the unique features of turbulent flow? before we answer that question, let's check two simultaneously occurring turbulent flow patterns. The first turbulent flow pattern is chaotic fluctuation created by swirling structures of different sizes. These chaotic fluctuations are always three-dimensional and always unsteady and always unpredictable. It's safe to say that turbulent flow is always three-dimensional and unsteady. Even though the turbulent flow has its unique chaotic fluctuation pattern, but it also has determined flow pattern that would be the bulk or mean flow. For example, when the current out of the hose, we can tell the mean flow is moving forward, which is represented by the streamline, the black parallel lines. So these two simultaneous occurring turbulent flow pattern, one mean, other one fluctuation, give us an idea on how to describe the uniqueness of turbulent flow. How? First, we introduce Reynolds decomposition, which is a mathematical technique to separate the average value of a quantity like a velocity, pressure, temperature from its fluctuation. Therefore, an instantaneous physical variable is represented by its average component plus the fluctuation component. These two plus give you the realization about instantaneous velocity and the temperature, averaged velocity and the temperature. The difference would be the fluctuation of the velocity and temperature. Second, we can introduce more variables to define or to describe turbulence. A, we already know the averaged mean variables. B, we already define fluctuation variables. C, we define turbulence strength, which is a root mean square, and turbulence intensity by comparison between the turbulence strength with the averaged turbulent flow velocity. D, turbulent kinetic energy, K. And lastly, turbulence dissipation, epsilon. Remember, when we define viscous dissipation, we stated that due to the friction, it creates the heat which dissipated into the fluid, into the flow wasted. That's why it's called viscous dissipation. Turbulent dissipation has the similar concept, but the heat created by friction is between those unique turbulent swirling structures between ides. F. At this point, we should have a general idea on how to study turbulent flow. First, we use the 5 governing equations to describe turbulent flow and laminar flow. For turbulent flow, we introduce the Reynolds decomposition to separate the averaged value from its fluctuation value. Third, we would do time average on the governing equations, and then solve the time averaged governing equations to get the mean variables for the mean flow. Once we get the temperature profile, we're able to calculate the heat transfer coefficient, then heat flux, and then heat rate to reach our ultimate goal. The following question then is raised: how to do or how to get the averaged governing equations? We have to follow the basic averaging rules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to do the averaging. Classic example shows you how to do the averaging, but we jump to the conclusion directly, which is compare the average equation with the original equation. You have noticed the average equation, time average equation, also called Reynolds average equation, same thing. Okay. So the green color equation represented the original ones. The blue color equations represented the averaged ones. By comparison, we noticed that all the averaged equations dropped time-dependent term. But due to the nonlinear term, they created new variables. 1, 2, 3, 4, 5. Now we're in trouble after doing the averaging, because originally we have full unknowns, full equations. Problems are closed, meaning we can get a solution. Now we have still have 4 equations, but we have a new unknowns. So we could not get a solution. Therefore, in order to close the problem, to get a solution, we need to add additional equations. How many? At least we need to add 5 additional equations. This process, we call it turbulent modeling. For example, we give you our additional equation just to show you what does it look like in this equation. This is the average temperature gradient, and this is turbulent diffusivity, and this is turbulent conductivity. Finally, the new created variable after doing time averaging has a special name. It's called eddy over Reynolds stress, and this is called eddy heat flux. In the future, if you read research paper, you will run into them when the convection involves turbulent flow. Finally, we take final look at the average governing equation by checking its benefit, challenge, and compromise. So this is a plot represent the temperature, and this is distance, and the black lines represent instantaneous temperature, and the pink line represent the time averaged temperature for the mean flow. The benefit using the averaged governing equation is we can solve for mean temperature profile, then get our heat transfer coefficient to reach our automated goal. The challenge using averaged governing equation is when we do the averaging, it creates new variables, so we need a turbulence modeling to close the problem. Third, then what is the compromise using the averaged temperature equation? When we do the time averaging, another benefit is drop the time dependence. Then it's also compromised because we lost that information about the velocity field and the temperature field. Another compromise is, since we did the averaging, we will lose the small scale turbulence structure. This can be seen from the instantaneous velocity field and time averaged velocity field. By comparison, you notice that the small structure of turbulence is gone. At this point, we better stop. We've covered topic 3. Hopefully, you're able to answer very basic questions about turbulent flow and convection. What we did not cover is detailed turbulence modeling and their equations, numerical simulation with the different methods, and turbulence theory. Even today, we still face a grand challenge to study turbulent flow and turbulence. These two famous scientists, and they ask the same question to God when they go to heaven, which is, why turbulence? What is turbulence? This is to tell you how complicated the turbulence flow is. Okay. Now we complete Advanced Convection Part 1, Governing Equations. This is the beautiful summary and outcomes of concept, variables, scales, and equations. Now we end Advanced Convection Part 1.